an astronomy and computer science researcher at University of Washington. And I've been working on the scikit-learn project for the last couple of years. And basically, scikit-learn grew out of NumPy and SciPy. It's, the scikit was this idea of kind of taking more specific scientific code packages and growing them out of SciPy and making them affiliated with SciPy, but in a way that could kind of be a little more dynamic and grow a little more quickly than SciPy. And scikit-learn started a few years ago, and since then has had a really active development team. It's pretty amazing to check that out. If you want to read more about it, you can go to the website, scikit-learn.org, and it should pop up there. Yeah, so there are a lot. There's a lot of interesting information here. There's example galleries. There is narrative documentation. There's documentation about everything in the package that we're going to be talking about today. So it's a really good resource. Check that out sometime. For this tutorial, hopefully you've already had a chance to go to my GitHub page where I have all this on here, and hopefully downloaded the notebooks. And everything here we're going to do is going to be run on IPython Notebook. So just really quick, I want to show you how to get this started. If you go to a terminal, I'm going to shut it down because I don't need it right now. If you go to a terminal, and let me make this bigger. So I'm in the directory of this scikit-learn PyCon 2013/notebooks. And in that directory, if you type IPython notebook, then that will start the notebook server if you've set everything up, and it'll pop up on a web page with this opening page. So does everyone have that set? Have that open? All right, good. So we can get started. Let's start by clicking on the first notebook, the preliminaries, and it should open up to a page that looks a little bit like this. Everyone's good? This is awesome to have so few technical problems. You guys are all really well prepared. Congratulations. So just a brief outline of what we're going to do today. This is an introduction to machine learning and to scikit-learn. So there are two kind of main components of this tutorial. I want to give everybody here kind of a basic idea, a basic intro to the concepts of machine learning, so that the kind of thing that apply not only to scikit-learn but to any machine learning library or any machine learning, any scientific package you'd use out there. But also give you an introduction to how scikit-learn can be used with those introductory concepts to do some interesting problems. And the problems, we're going to start very basic today and kind of move into more intricate examples. And just because of time constraints, we're not going to do anything really big. We're not going to do anything where you have to run the code for 5 minutes, because that would be 5 minutes of sitting and doing downtime. But all the small data sets that we're using today, all the small problems we do can be generalized to larger problems. So my hope is that by the end of today, you could go home and with the knowledge you pick up and with the ideas about how to use scikit-learn, you can go to your own data sets and think about them as a machine learning practitioner. Think about them in a way that you could go and do some interesting things with your own data. So hopefully that will happen for you. And hopefully I can bring all of us to that place. So let's take a look at this, this introductory stuff. So essentially the schedule, I did this wrong. I assumed we were an afternoon tutorial, but we're a morning tutorial. So this is from 9 o'clock to about 10:30. We're going to be doing part one, which is kind of getting started. We're going to talk about loading and representing data, the basics of machine learning and the scikit-learn syntax. And then we're going to go into a few simple examples of what we call supervised learning, and then into unsupervised learning. And we'll get into more of what those mean later on. There will be a short break from, again, this is wrong, so I'll do math in my head, 9:30, 10:30. We're going to do a short break from 10:30 until 10:30 until 11:50, and then we'll have another hour and a half session in the second half. And in the second half, we'll get into some of the really interesting stuff, which is how to validate and test models. So once you've put together a scikit-learn model, how do you tell how well you're doing with that? And how can you predict how well you're going to do on a new data set? And then if we have time towards the end, this might go a little long, but if we have time towards the end, we have a couple interesting examples from astronomy, from image classification, and from other things. So I purposely put more material in here than I think we can fit in 3 hours. And the reason is I want you guys to be able to take this and work on some more things at home if you have the chance. Okay, so we've already been through some of the preliminaries. This is just what is required for the tutorial, Python, several packages, and hopefully you have that all there. So just to make sure you have the right versions installed, we have this here. So if in IPython Notebook, the way that you run code is you go to the cell and you press Shift and then Enter. And if you press Shift Enter, it should execute this code and tell you what versions of NumPy, SciPy, Matplotlib, and scikit-learn you have. So hopefully if you have NumPy 1.5 plus, SciPy 0.10 plus or so, Matplotlib greater than version 1, and scikit-learn 0.12, you should be fine. Is there anyone who has older packages right now? Maybe Olivier, you could talk to them. A few people with older packages, raise your hand. For the most part, you probably should be all right with older packages. I don't think there's a lot of the newer stuff we're using, but just be aware that some of these things might not work. Another thing I want to share with you is some useful resources. This is just to learn more afterwards. I showed you the scikit-learn website. That's a nice one. The Matplotlib website is really interesting. If you click here, this is just for the data visualization stuff, especially if you click on the gallery tab in the Matplotlib website. It's really interesting. They just have thumbnails of all sorts of different types of plots that you can do with Matplotlib. And there's so many thumbnails that it'll probably take a while for them to load on your conference wireless here. But any of these, if you say, oh, I'm interested in how this picture was made, you can click on it, and it'll give you the source code for that. So that's a really, really good resource for this sort of thing. So that's all the basic intro stuff. And now let's close this. Let's close this preliminary notebook, and I'm going to close some of these other sites too because I don't need them, and go on to the introduction. So in the introduction, I want to give you an idea of what sort of tasks qualify as machine learning problems, first of all. I want to show you some simple examples of what machine learning might look like. And then we're going to go through some really basic stuff on creating and manipulating NumPy arrays. This should be review for a lot of you, but I just want to get it out there so the stuff later doesn't look completely foreign. And then some of the basics of doing some plots in Matplotlib. We're going to use that later as well. So when you're, so let's start out by asking what is machine learning. So machine learning is essentially a way to create computer models that have tunable parameters. And those tunable parameters are tuned by looking at data. And then once you've tuned those parameters, you can look at other data and figure out what's going on. So the reason this is called machine learning is because once we set up these models and give the computer some data, then the computer learns from that data, learns more, and is actually able to train these models to tell us more about data that we don't know things about. So that's a little abstract right now, but we'll get into the details of it here. So first, when we're using IPython notebooks, one thing that's helpful is to do this pylab inline thing. That'll mean when we execute that, that'll mean that all images that all figures that we plot will show up within the notebook. So you'll notice on almost every notebook we do, we'll start out with that somewhere. And I made a little example script of a machine learning problem here. So we're gonna import this function that I wrote, and it will do a quick learning problem and show the results. So these are the results right here, and let's see if I can zoom in and make it a little bigger. So this is an example of a really simple machine learning problem. So we have a two-dimensional data set with some labels, and we've said, this cluster of points has this label, this other cluster of points has another label, and we've asked scikit-learn to find a boundary between these. So you might think to yourself, well, this is pretty simple. I could just plot this up and draw the boundary myself, right? But in 2 dimensions, it is simple. But as you start getting to very high dimensional data, up thousands of dimensions, hundreds of dimensions, this sort of thing gets pretty difficult to do by eye, by hand. But the machine learning tools scale up and can do this sort of thing in any number of dimensions. So why would I call this a learning thing? So basically, we've given scikit-learn this data. It's learned this separator. And now if we had some new data, say if we added some points out here, and we wanted to know, are these blue points or are these red points? We don't have labels for them. Then the algorithm would be able to tell us whether those points fall in the blue category or the red category. So that's what machine learning comes down to. It's simple things like this. And this is an example of a classification problem where you have discrete labels for each of your data points. So the key here is that we can generalize based on data that we've seen, and from that generalization we can predict what categories new data falls in. So just in case you're curious, the script that plotted this is in the directory here, and you can type load to load it up. Use the load magic, and this is what we did. We basically made some data. We instantiated this classifier, the SGD classifier. We fit it, and then we plot the results and plot the prediction. So we'll get into more of how that works later, but just so you know, every figure that I have in here, the source code is available, so you can look through and see how it's done. Another common machine learning task is regression. So here's an example of regression, and you might have heard of regression in the context of just fitting a line to data. And that's essentially what regression is in the simplest case. We have data where we know the x and the y values, and we ask for a continuous model that given x, we can predict what y is. So again, this is an example of tuning the model. The model learns from the data. And then if we were given new data with some x values where we didn't know the y values, we'd be able to predict where on this line the data lies. So again, you might think this is pretty simple, right? You could plot up 2 dimensions and draw a line. You can do that by hand. But think about doing this with thousands of dimensions. If you have thousands of attributes and you're trying to predict, say, we'll see later, if you have several attributes about what a house looks like and you want to predict how much the house is going to sell for, it's a lot more complicated than just drawing a line through data, but the principles that apply here also apply in those higher dimensional cases. So any questions at this point? I don't want to just talk at you guys the whole time. Feel free to interrupt me if anything comes up that's confusing, or if there's anything you want more clarification on. So really quickly now, before we move into some more sophisticated examples of machine learning, I want to show you just a couple of the tools of the trade that we'll use within Python. And this is stuff that hopefully looks familiar to you. But if not, then you'll see what this looks like. So NumPy is our array library. And if we want to generate a random array, we can do something that looks like this. Random.random, and then the shape of the array here. And here we did a 3x5 array. We can also do arrays with more than 3 dimensions. We can basically make them as big as we want. And this is just a good way to generate random data if we need to try out a model and we don't really care what we're putting in. We just want to see that it works with the data. In NumPy, you can, let me go back to the 3x5 array here. You can access elements using this indexing notation. So the 0, 0 gets the 0th element there, the 0.43. And then we can get the first row, 0 index. So you can see that matches the second row from the top, which is, because we count 0, 1. Same thing, we can get the column by using the colon operator. And similarly, we can do the transpose using this x.t. So this is kind of the stuff that we'll use a lot of the time. And another thing that's often useful is turning a row vector into a column vector. And the way that we'll do that is by using this colon and new axis. So we're basically saying, take the whole row vector and put it in this dimension, and then add a new axis in this dimension, and you get a column vector out of that. So basic NumPy stuff. If you want to learn more about NumPy at some point, there's actually there's this website called scipylectures.github.com. It's really useful for doing any sort of stuff like this. And it has everything from getting started on Python all the way through creating and manipulating numerical data, plotting, and then I think there's even a scikit-learn tutorial somewhere down here. 3D plotting, yeah, here's the scikit-learn tutorial. So lots of good info there. scipy-lectures.github.com. So more good stuff to look at when you go home. So the other thing that we might use sometimes in scikit-learn is sparse matrices. And this is in the scipy package. And what you can do is, if you create a sparse array, so here what we've done is we've created a 10 by 5 dense array. We've taken everything that's less than 0.7 and set it equal to 0. And when we do that, we get this sparse array that has a lot of zeros in it. Now this is not a very compact notation. Like imagine if you had a million by million array, but 90% of the entries are 0. You wouldn't want to explicitly store all those zeros. So what you can do is turn it into a sparse matrix, and this is what the representation looks like. It essentially only stores the non-zero entries. And there are a lot of estimators in scikit-learn that can use these sparse matrices, and it's really useful for larger problems. And if you want to go from a sparse matrix and recover the dense array, you can use this toArray function, and it gives it right back. So we won't be using, I don't think, we probably won't be using any sparse matrices in this tutorial, but it's just something good to know about for the types of big data sets that you might come across in your own work. There are other kinds of sparse matrices as well. This is called the LIL matrix, which stands for lists in lists. So the advantage of LIL matrices is you can use item assignment like this. So you can create an empty one and then assign values and then print the result. But the issue with LIL matrices is they're very slow. They're flexible, but they're not as fast as CSR matrices. So often if you build up one of those, you'll convert it to CSR, and then you get the nice fast matrix like that. So there are a number of different sparse formats that you can use. You can read about those in SciPy, but it's something to be aware of if you start applying scikit-learn to bigger data sets. Another piece of this new tutorial that is important is matplotlib, and this is the plotting library that we'll use. So matplotlib we usually import like this. This is kind of a standard, matplotlib.pyplot as PLT. And you'll see that all over the Python universe online. People use that as kind of a custom. And plotting is pretty easy. So if we want to plot a sine wave, we use this linspace thing. So this says we're making 100 evenly spaced data points between 0 and 10. And then we'll plot x versus the sine of x and see what that looks like. So we get a nice line out as we'd expect. Scatter plotting is the same. If we take 500 normally distributed points in x and 500 in y, and we can scatter the two of them, and it looks like that, as you'd expect. And we can also show images. So here we're going to do something a little bit tricky. We have we make another linspace of x 100 points between 1 and 12. We use this trick, this new axis trick, to make y a column vector. And then we multiply them together. And this will kind of multiply the row and the column vector together and create a two-dimensional array. And if we want to visualize that array, we can use the imshow command, which is image show. And this is sort of what it looks like. Another way to do it is to use the contour command. So this is a way to visualize two-dimensional data. So we'll be using some of this stuff throughout the tutorial, and hopefully all that looks familiar to you. And if not, there's some good resources online, and that's SciPy Lectures to learn about it at a later point. So I'm going to leave this page now, and we're going to get into something a little more interesting. Now we're getting into the scikit-learn stuff. And one of the nice things about scikit-learn is it has a bunch of data sets built in that we can use to try out models and see how they perform, and then from there generalize it to our own data sets. So we're going to talk right now about representation and visualization, and also downloading of the scikit-learn data. And so in this section, I'm hoping that you'll, by the end, know the internal data representation in scikit-learn, how you represent data so that scikit-learn through the computer can do work on it. Also, I want you to know how to use the dataset loaders. I want you to know how to turn the image and text data and other kind of interesting data formats into matrices that we can use for machine learning. And also know how to use matplotlib to visualize some of these things, which I guess we went over a little bit. But so basically, data in scikit-learn is almost always in the form of a two-dimensional matrix. And the matrix that will look like matrix or a two-dimensional array. And the array shape that we have is number of samples by number of features. So when I say number of samples, I mean, for example, in my field, if we're looking at galaxies, the number of samples would be the number of individual galaxies that you're looking at. And the number of features would be the number of observations of each of those galaxies. So, for example, you could observe the galaxy through a red filter, a blue filter, a green filter, and you have these different fluxes at different colors, and those are the features of each galaxy. And then to put that data into scikit-learn, we put that in a matrix that is that's two-dimensional, number of samples by number of features. Okay. So a simple example of this is the iris data set. And just to give you an idea of the kind of stuff we're looking at, there are several species of irises out there. I just loaded some images here of them. And if you look at these pictures, these are actually three distinct species of iris. And to the untrained eye, they might look pretty much the same, right? So if we're going to do, what we're going to do here is design use a quick machine learning, a scikit-learn estimator to help us determine, given observations of an iris, what species of iris it is. So I want you to think about this for a second. We need this 2D array of n samples by n features. So in this case, what does the n samples refer to? What are the samples? Yeah, the number of flowers that you've seen, right? And then a little more difficult question, what are the features here? What could you imagine the features being for this iris set that you're observing? No fair scrolling down. Someone said color. So lengths of the petals, yeah. You might, if you were trying to be really sophisticated, you might actually imagine the features being the pixels on this image, right? You could take the color or the intensity of each pixel on this image and feed it into an algorithm. That would get a little more difficult. But yeah, things like you observe the colors, you observe the length of petals, the length of sepals, the length of various pieces of the iris. And that's exactly what this simple data set is. We have the features in this. We have the samples are the number of flowers that we're looking at. The features are the lengths and widths of various pieces of the flowers. And then there are labels, which are the species names. So let's take a look at this, how to get this in scikit-learn. Scikit-learn has this datasets module, which is really, really interesting. You can peruse it later. But if we use the load iris function and load it like that, and then the thing that's returned is a bunch object. It's kind of a a bunch of data all in one object. And if we click keys, we can see what's in there. We have target names, we have the data, the target, the description, and the feature names. So let's look at the data and see the shape. Again, we said that the shape is n samples by n features, right? So what we have here are 150 samples. We have 150 different flowers and 4 different features. And just looking at the first value here, we can see the features for this are just real numbers. They're lengths, I think, in centimeters. And now the target is what tells us what kind of iris this is. It tells us the species of iris. And we can see that the target, as we'd expect, matches the number of samples. So for each sample, we have 1 target value. And just to take a look at this, we can print out what the target values are. And it's basically 0, 1, or 2. So to map those to the actual names, we have this array called target names, where it says it's 0 is Setosa. Let me scroll this up. 0 is Setosa, 1 is Versicolor, and 2 is Virginica. I'm going to toggle the header and make this a little bigger. So the data here is 4-dimensional. So if we had a way to plot 4-dimensional data, we could visualize the whole thing. But often we just need to look at 2 components at a time. So here I've set the x-index and the y-index. These are the 2 components we're going to visualize. Made a little formatter, and then we're going to scatter plot the data and make a color bar and label the axes. And this is what it looks like. Now you can see that with these first 2 features, it's kind of hard to distinguish between the irises, right? But take a second now, and there are 4 different features you can use. So try plotting some different combinations of features against each other and see if you can find some combinations that do separate the data pretty well. So for example, you could just change y-index to 2 and rerun this code. Then you have something that's a little better than the 0 and 1, right? If we do 2 and 2, it looks silly. So what you're doing right now is something, it's a process called feature selection. And this can be really important when you have high-dimensional data to select the features that are the most useful. In the case of 4-dimensional data, it's a simple exercise. But when you have larger data dimensions, it can be an interesting thing. And right now we're doing it manually, just by trial and error, but there are actually algorithms out there that help you do feature selection. So did anyone find a really good combination that helps distinguish the data pretty well? Which one? 2 and 3? Let's take a look at that. Yeah, that's pretty good. So 2 and 3, you can see that the blue are really well separated and the green and red are a little bit confused. So yeah, this is feature selection, and like I said, there are algorithms that do this automatically, but it just kind of gives you an intuition into what's going on in those algorithms. So just so you know, there's more than just the iris data set available. If you go down here and import the data sets and then do datasets.fetch, start typing fetch and then type tab, you can see all the different data sets that are fetchable. These are ones that are actually downloaded from a web service. So if all of you start fetching data right now, the network's going to die. But there are also these load data sets that can be loaded. These are ones that are included in the scikit-learn distribution, and you can play around with them. And there's some interesting ones in there. All these data sets that are fetched and saved are saved to your home directory. So if you print this get data home thing, it'll tell you the directory on your computer where this data is saved. And I'm just going to list that right now so you can, oh yeah, that's the wrong one. I was doing this on another computer. So if I list that right now, you can see that I've I've downloaded a number of these data sets over the last couple months and used them. So that's the data fetchers in scikit-learn. So those can be useful. Let's look at another data set example. And this one is a little more involved than the iris. The iris had 4 dimensions, and this is a data set that has 64 dimensions. So it gets a little more interesting in the visualization. This is a digits data set. So what we have is we have some observations of handwritten digits that we can use to try to basically do handwriting recognition. So we look at the keys. We have these images, data, target names, description, target, very similar to what we saw in the iris. But if we look at the shape of this, the digits data, the shape is 1797 by 64. So we have 1700, almost 1800 samples, and we have 64 values. And if we look at the values, it's a little bit difficult just from that to interpret what they might be. But there's also this images array right here. And the images array is 1797 by 8 by 8. And this is one quick little detail that I think is kind of interesting. That it seems to have 2 copies of this data here, but really the data is not copied because that would be kind of inefficient. If you reshape the digits data or the images data to the size of the digits data, you can see that it's all equal. So it's kind of showing the same data set, but it's also actually pointing to the same memory. So you can get into the guts of the NumPy array interface, and what we have here with these long integers here is actually a memory location where this array is stored. And you can see that the memory location of that array for the 2 is the same. So anyway, it's not super important, but it means that the data is not being copied in 2 places. It's the same data pointed to by the 2 arrays. But let's quickly visualize this data. So what we're going to do here is set up a figure, and we're going to adjust the subplots, basically kind of line up the subplots in the figure. And then we're going to go through 64 different digits. We're going to add a subplot on an 8 by 8 grid. And then we're going to use that IMShow command, showing the image. We're going to show the digits image and then label it. So let's see what comes out here. This takes a little bit to run because it has to render a lot of pixels. But this is what the data set looks like. So you can see we have basically handwritten digits. We have 8 by 8 pixel grid pictures of them, and we can visualize them like that. So now the interesting thing here that sometimes it's hard to wrap your mind around is that this is 2-dimensional data, right? 8 by 8. But when we put it into scikit-learn, we want that 2-dimensional data to kind of be stretched out into a 1-dimensional array per image. So that's exactly what that data does. It basically reshapes the image, and you can think about each pixel in that image as just one in an array string. So what we get out is a number of samples by number of features array, right? So each pixel value, how much ink is in each pixel, that's our feature in this case. And that's a pretty common feature choice for images. So really quick, to give you an idea of what it's like to work with this data, I want you to try something on the faces data set. So this is a fetch operation. It fetches, I think, about 1.7 megabytes worth of data. So if you haven't already run the download script and downloaded this, it might take a little bit. But I want you to take a second here and really quickly fetch this faces data, take a look at what's inside it, and then try to do a visualization similar to these digits images here, and we can see what the data looks like. And while you're doing that, I'll walk around. So raise your hand if you have any questions on that. It'll take about 5 minutes for this. One thing you might find useful is actually copying and pasting this from up above and just modifying it. You can feel free to chat with the person next to you if you need a little help with this or want to offer some help. You having trouble downloading? No fetch. Well, since a few people are having trouble with the fetch, I'll quickly just show you how I imagine going through this. So you can do the fetch Olivetti faces here. Get the data that way, and hopefully you downloaded it before, so you don't have to go through the network right now. The keys are similar to before. The shape of the data is 400 by 4096. So here we have 400 samples and over 4,000 features. And similarly to the digits, there's an images attribute as well, which is 400 by 64 by 64. So they just reshaped the data. And then I just copied what we did above for the digits, but I replaced the digits data by the faces data, looked at the images, and then we actually don't need this label, do we? And I also changed the color map to bone right here, which is a little nicer than binary for the faces data. Sorry? How did you know the figures are going to be the same size? Yeah, that's a great question. So his question was, does scikit-learn force you to have the same number of features in each row? And the answer is basically yes. You need your data to be, you need your features to each kind of refer to the same thing. So in the case of the iris data, the first column was all sepal measurements, and the second column was all petal measurements, right? In the case of these images that we're looking at, the first column is always the upper left pixel. The second column is always the next pixel over. But you're probably thinking about the fact that in the real world, images don't behave that way, right? So this is an interesting piece of machine learning. You need often a big piece of it is getting your data from the real world into the format that can be recognized by a machine learning algorithm. And all machine learning algorithms need the features to be kind of related to each other, to refer to the same pixel or refer to the same measurement. And so, for example, if you're given a picture of a crowd and you want to find people in that crowd, you need some sort of image processing algorithm that will find the faces. And that's something that it's a little bit of a different paradigm, but one way you could imagine doing that is, say you take a bunch of little 8x8 boxes across the image, right? And they might overlap, and then you train a classifier and say, this is what a face looks like, and this looks like someone's pant leg. And you take all all the things that you know are faces, and then you can train a classifier to actually recognize which of those little boxes throughout the image has a face in it. And then once you do that, you have your data, and you could do some sort of learning and look for the match of someone's face. There are other ways to do similar things, but so basically that's a really good point, that the features in most machine learning algorithms have to be uniform. They have to be the same length, and getting your data to that point is sometimes a challenge. Any other questions right now? Were people able to get this showing, or are a lot of people? Are there many people who weren't able to download the data because of the wireless? Several? Okay. Well, we'll move on from that right now. We've looked at data in scikit-learn, and now we're going to get into the interesting thing. Now that we know how to run the Python stuff, now that we know how to get the data, we can talk about the basics of machine learning. And here in this, we're going to talk about the general concepts, kind of the 101 level concepts of machine learning. And we're going to look at the basic categories of machine learning. There's supervised learning, there's unsupervised learning. Classification, regression fall into supervised learning. Dimensionality reduction and clustering fall into unsupervised learning. Toggle header. Why did that come back? There we go. I want to show you the basic syntax of the scikit-learn estimator interface, and this is kind of what you'll do everything with if you work with scikit-learn. And then we'll talk a little bit more about how to extract features from real-world data, the way that Matt was asking about. So quick review, we saw this before, but machine learning is about building programs with tunable parameters, where those tunable parameters can adapt to previously seen data. And everything's in the n samples by n features, 2D matrices. And there are two types of learning, two basic types of learning that we'll look at, supervised and unsupervised. So supervised learning is like what we saw in the last slide, where you have data that you've observed and the data has some sort of label. The label might be the species of iris, the label might be the person who's in the image, or the number that's written in the digit image. So supervised learning, when you hear supervised learning, think labeled data, right? And there are, so a few examples that you might do of supervised learning are, given a multicolor image of an object through a telescope, try to figure out whether that object is a star, a quasar, or a galaxy. This is something that comes up in my field. Given a photograph of a person, identify the person in the photo. We saw some of that type of data earlier. And then recommender systems. Given a list of movies a person has watched, recommend a list of other movies they might like. And this is kind of became popular in the Netflix prize several years ago. So what these have in common is you have this known training set with labeled data, and then you have an unknown training set, a person for whom you don't know what movies they like, and you want to predict what those data are. So unsupervised learning is different, where supervised learning deals with labeled data. Unsupervised learning deals with unlabeled data. So imagine you have a collection of faces, of pictures of faces, and you have no idea whether they're the same person or different people. And you want your learning algorithm to say, are these faces the same or are they different? Is this multiple people or is it the same one? You don't have any labels on the data, and an unsupervised learning task will do that sort of thing. So some examples. So given observations of distant galaxies, so an unsupervised learning task would be to figure out what combination of features is most important in distinguishing between different clusters of galaxies. This is kind of this feature selection thing we saw before. Or, for example, given a mixture of two sound sources, can you separate it out? So if you have somebody talking over an AC/DC recording, can you take that and without knowing anything else, just separate it and pull out the person's voice and pull out the AC/DC song? And surprisingly enough, you can actually do that. It's a really interesting problem. And if you're interested in that, you can look at blind source separation. And there's some algorithms in scikit-learn that can do that. Similarly, given a video, if you isolate an object that's moving through it and kind of categorize it in relation to other isolated objects, what these all have in common is that there's no labels on the data. You don't know what you're trying to predict. You're just asking the machine learning algorithm to basically say, what's interesting about this data? Can I find a cluster? Can I find a projection? Or can I find an object that's interesting?
Is that known? He used it before. Is that just easy?
Yeah, that's just unknown. So he asked in the blind source separation, does it have to be a known thing that you're separating out? And the answer is no. Basically what you can do is, if you set up 2 microphones in a room, you have 2 independent data sources. And if there are 2 people talking, then you can often actually pull out both of the independent signals. And it's a pretty interesting problem if you want to look into it later. So, so this is what the scikit-learn interface looks like. If you import some sort of model that you want to use, and here's a simple example, linear regression. And the first thing that happens is you can instantiate the model. So a model is a class, and then you instantiate that class, and that's your model that you're then going to train. And if we print this model, we can see that the linear regression has a couple what we call hyperparameters. These are things that are set before you see the data, before you train on the data. And in these models, there are several functions, there are several methods that you can use. So in all estimators, there's something called the fit method. And this is where you pass it your training data, or you pass it your data that you're interested in. And then the model, depending on the model, it'll do something in the background and try to figure out how to best fit that data. And then in supervised estimators, remember supervised is where you have label information about the data. There are things like predicts, where you can predict the labels for new data. There's predict probability, shortened to proba for some reason. And that's where you can predict kind of probabilistic information about new data. And then there's something called score in many estimators, which gives you a 0 to 1 score of how well you've predicted your new data. In unsupervised estimators, there's something called transform that we'll go into that a little bit later. Transform and fit transform and how those are used. So just to visualize this a little more, I made some figures of some diagrams. These were actually adapted from something Olivier put together. And these are some diagrams of kind of the flow of what machine learning looks like. So a supervised model, you have this the training data on the top left, the text or documents or images, and then you have to somehow turn that into feature vectors, like we were talking about, somehow find uniform features within those. And then you also have the labels. And from these, you train your machine learning algorithm. That's that model that we created. And we call the fit method on it to create that. And then given some new text or document, you generate the feature vector that matches those other ones. You put that together into this predictive model, and then you get out your expected label. So that's kind of the flow of a supervised machine learning problem. If we scroll down a little bit more, we can annotate this, and basically we see that these are the scikit-learn functions that we'd kind of call to turn raw data into features. There are some vectorizer classes that work for text. They sometimes do some more sophisticated stuff to kind of mangle your data into the form you want it. Then you call fit to create the model, and then call predict to get the new label. In the unsupervised learning model, if we run this right here, you'll see the difference is that we've taken out the labels completely, right? We don't have any information about labels. So we vectorize the training data, we put it through an algorithm, and we get some sort of model out there that predicts the clustering or predicts the relationship between the data. And then when we put new data in, and through the model, it'll tell us about the likelihood of the data, or the cluster ID, or the low-dimensional representation of the data, or anything like that. Unsupervised learning is a little more wishy-washy. It's hard to exactly define what you want to get out of it. And depending on what sort of learning methods you use, you might have different goals. Supervised learning, you're pretty much always looking for some sort of expected label prediction. Does that all make sense? Anything unclear there? Yeah.
You're going to cover this later, you can tell me, but it looks like on the fit you pass in all of your training data. Do you iteratively pass in data, like to get more labels later on?
Yeah, the question was, in the fit here, it looks like we're passing in all our training data, and he was asking if there's a way to iteratively pass in more data. And the answer is yes. In some models, it's called online learning, where you can you can pass in more data as time goes on and maybe iteratively update your model. And there's some models that works really well on, and some that it doesn't work so well on. Scikit-learn, for the most part, right now doesn't have much of an interface for online learning. That's one of the API enhancements that we want to work on in the next couple of years. But it's definitely out there. Yeah. Other questions? All right, let's move on to see some examples of this. Oh, again, if you want to see the code for how we generated these flowcharts, it's just you can load it in here, and it's basically just a whole bunch of rectangles and circles and polygons and fancy arrows all put in the right place to make those. So not quite as easy as doing it in PowerPoint or something, but I think it's cool. Anyway. So returning to feature extraction, actually we talked about a lot of this, just how you need to basically take your real world data and get it into labels where each feature refers to the same type of thing. And one thing that's interesting is categorical features. Let's say you added to the iris data set the color of the flower, and you knew the flower was red, blue, or purple. You might think a good way to do that would be to add a feature that corresponds to color, and maybe red would be 0, and blue would be 1, and purple would be 2. But it turns out that's not very good, because most learning algorithms tend to assume that features kind of are in an ordered set. So a distance is a good example, or a length of a petal. It's kind of related along a line. It's ordered, right? But these colors are not necessarily ordered, or you could think about it in rainbow order. But if you had other categorical features that weren't necessarily ordered, it's not a good way to go. So one way you can do it is to actually make a feature for each categorical value. So you might have a feature that's purple, and it's 1 or 0, true or false. Blue, 1 or 0. Red, 1 or 0. Now, if you start thinking about having like 1,000 categorical features that are 1s or 0s, that's where we get into sparse data, where sparse matrices are interesting. For text documents, sometimes text classification is a really interesting problem, but you might wonder, how do you get a text document into something that has a uniform number of features per document? And one approach you can use is called bag of words, where you basically count the number of occurrences of each word in the document. Or you could count the occurrences of pairs of words throughout the document. And basically, it takes some thought to figure out how to set up your features, but you can do it with almost anything. And like we were saying with images, if you have non-uniform images, you have to basically figure out how to rescale them, or figure out how to extract local features or transform the signal or use wavelets, things like that. There are all sorts of approaches to that. So any problem you have, if you're wondering how to get out features, there's probably some information online that you can find in various tutorials about how to deal with these types of data. So just remember, everything you have, it needs to be down to a number of features, number of samples by number of features matrix. And then you can go ahead and do scikit-learn, do machine learning on it. So in the next couple of notebooks, we're going to explore a few simple examples of classification, of regression, of dimensionality reduction, and clustering on some of these data sets and some other ones. And all this preliminary stuff that we've been working on for the last 45 minutes or so, we'll be able to use that now. So let's move on to number 4. So this is a regression example. And I think regression is really, really interesting because it's the main type of machine learning that I use in my research. I'm looking at a lot of astronomical images and trying to figure out things like galaxy masses or distances to galaxies or things like that. So what we're going to use here is something I alluded to earlier, which is housing data. So through this, I'm hoping that you'll know how to use, basically instantiate a scikit-learn regressor, how to use the fit method, how to use the predict method, and learn from it. So the first thing we're going to do, we're going to load this Boston data set. And this is basically, this is a bunch of data from the early 80s on neighborhoods in Boston. And there are attributes of each neighborhood. Let's run this down here. Yeah, there are attributes of each neighborhood, basically the per capita crime rate, you can read all this, nitric oxide concentration, distance to employment centers, accessibility to highways, and then the target value is the median price and that home price in that neighborhood. So the idea is here we could wonder if, given these attributes of these neighborhoods, could we predict what we'd expect the home price to be in a new neighborhood? And you can see where this could be interesting for realtors and those sorts of things. So one thing that's often interesting to do when you're confronted with a new data set is just to visualize the data. So here we're going to do a histogram with the hist function of the target value, which is the prices. And we see this histogram right here. And now it's clear that this was taken in the 80s because this median home price in Boston is $20,000, which is a little different than today, I think. I mean, I'm not in the real estate market over there, but. So let's go back to this feature selection thing here. And really quickly, I want you to try to do a scatter plot of some of the data features versus the target values and see if there's anything that seems to correlate really well with that. So this will use the scatter plot functionality that we saw before. So remember, it'll look like scatter x comma y. We have a lot of different features here that we can play with. Oh, that's an interesting one. So if we scatter data and then colon and the column number versus the target, and we see something like this. We can see here that this one's a categorical feature, so that might not be as helpful in defining the price. Whoops. So I found that, looking here, just the fifth column, column 5, tends to correlate pretty well with the target values, with the price. And if you look at what the feature name is on this is RM, which, checking above, we can see that that's the number of rooms in the house. So that makes sense, right? Bigger houses go for more money. So again, this is a feature selection thing like we've seen before. But we can, now what we can do is look at a simple linear regression model to try to predict the price of a new house. So from what we're going to do is import the linear regression classifier here. We're going to instantiate it. So we have an object of type of the linear regression class. And then we'll call the fit value on the data and on the target. So the first thing that's passed here is the matrix of attributes. And the second is the labels. And we'll fit that, and we see that we got something out. And now we can say, based on our model, let's see what our model predicts for our data, right? And now this is just a way to kind of visualize and see how a regression algorithm is doing. We're going to scatter the target data, the true values, versus these predicted values. And what we get out is something that looks like this. So we can see that the classifier does fairly well. I mean, it's at least correlated, the input and the output. And it'd be an interesting question to see if you could do better with a more sophisticated classifier. One thing about this is you can see on the high end, the predictions are biased low, right? And that might be a problem with or it probably is a problem with the model. The model's not able to capture that kind of turnover in the relationship between the features and the values. And I think if I were interpreting this, that it might be due to the fact that, like, once you get up to really expensive houses, it's kind of hard to predict, right? Because it's based on neighborhood, it's based on the size of them, it might be based on the schools that are in the neighborhood or things like that. And maybe it turns up and goes nonlinear a little bit. So we just used here a linear regression model. A more sophisticated model that we could use is something called a decision tree. And I won't go into the details of how decision trees work. You can read about that online. But the nice thing about scikit-learn is that once you know the syntax, you can try out any of these models and just see what comes out, right? So it's always a good idea to learn a little bit about what's going on in the background, especially for setting the options on these. But and I take a look at how we did that linear regression above, and try using this decision tree regressor to do the same thing. And let's see what comes out. And feel free to raise your hand if you're having any problems or need some help. Anything strange come up in that? Did anyone get that to run? Yeah, let me, this is my, my solution here. What did I do wrong? I forgot to import it. Yeah, so if you run this the same way we did before, you see that it's a perfect result, right? And so this shows you a little thing that it's a bit of a challenge in machine learning, which is evaluating how well your model's doing. The reason this is a little bit weird is because a decision tree regressor is something that we call an instance-based learner. So it basically stores kind of a library of all the training results. And when you plug in an unknown, it uses an algorithm to go through and compare the unknown to the training one and see which one is closest. But since we're testing this on stuff that it was trained on, of course the closest is going to be the exact same result, right? So it comes out and it looks perfect like this. Now this is not to say that the classifier is perfect by any means, right? What's happening here is it's overfitting the data. It's basically saying that for the things that I've seen, I can do that really, really well. But for something I haven't seen yet, it's probably going to be way off. And one thing you can do is play around with the decision tree regressor. And if you look into how it's implemented, we can change something like the max depth parameter and rerun it. And then you see you get something that's a little less perfect. Let's make it max depth 7, how about? Yeah, so that's doing a little more generalization. And this brings up the need for something that we call validation or cross-validation, which is when we evaluate a model, we want to make sure that we're not running into this sort of problem, right? Yeah, his question was, can we just give it a partial set from the data? And that's exactly what we'll do a little bit later. Essentially what we do is we train the model on part of the data and then evaluate the model on the rest of the data. And that gives us a better idea of how it would perform in reality. Yeah.
Incorporate randomization, regularization. You sort of stack on extra things to the models.
Yeah. So his question was: is it easy to incorporate regularization or additional features, that sort of thing, into the models? And the answer is for some models, yes, it is. We're not going to talk specifically about that in this tutorial, but on the documentation online on scikit-learn, you can learn about regularization, additional features, and things like that, and that's one way that you address some of this sort of thing. So, but yeah, so this is just to highlight the importance of doing good model validation, because if you went, if you were running this for your employer and you said, I can perfectly predict real estate prices now, you'd be lying because you can't. All right, so later in this tutorial, we'll get back to decision trees and kind of using some model evaluation techniques on them to figure out how we can do better. But for now, let's close this one, and we're going to move on to a classification example. And what's our timing? I guess we have about 15, 20 minutes till the break. So this is another supervised learning example where we're going to do classification. And this is going back to the iris data set that we saw before. And we're going to use something called a linear support vector classifier. So support vector machines are they're a really, really powerful method within machine learning. And this is a simple example of it, that they can be used to do some really interesting stuff. So I want to show you how this works, and then you'd be able to apply this to your own data and to other data sets. So again, we're going to load the iris data as we did before, and just to remind ourselves, what we have are 150 samples with 4 features, right? The lengths of the sepals and petals. And now we're going to, from scikit-learn.svm, support vector machines, we'll import this linear support vector classifier. That's what SVC stands for, support vector classifier. And if you're curious about how to instantiate this, one thing you can do is type in linear SVC and then the question mark, and this is in IPython or IPython notebook. The question mark gives you a little help menu with documentation on it. So SVC, we can put in a float penalty parameter. We can specify what loss we want, L1 or L2, what kind of penalty we want. We can do the dual optimization, the tolerance, multi-class, fit intercept scaling. So there are all these different parameters, different hyperparameters that we can adjust when we decide what model we want to fit. So this just, a lot of these things are described on the scikit-learn documentation, but I just wanted to make you aware that they're there if you're ever curious. So, so we'll instantiate this classifier, and we're going to use the L2 loss, which is just kind of a machine learning name for doing root mean square type of thing. And again, we'll print this classifier, and we can see what all these parameters are. We use mostly the default parameters, except for this L2 loss here. And just as before, we called X the iris data and Y the iris target. We'll go down here and we'll fit to X the feature vector first with the target vector second. And now one interesting thing to see is once we've done this, we can see some of the parameters that are learned by the scikit-learn model. So when you call this fit method, there's some sort of model specification, and then the model sets these tunable parameters on the inside that basically tell it about the data. And in scikit-learn, anything that is learned when you call the fit method has a trailing underscore here. So if you do CLF dot and press tab, it'll show you all the different things that are in there. And everything with the trailing underscore is learned during the training. So let's take a look at the class weight. We didn't use any class weight. Take a look at the intercept. And this is basically this is a generalization of if you're fitting a line to data, you have the y-intercept value. This is a generalization of that y-intercept to higher dimensions.
So if you were working with a very large data set and you had to do this fit and the model generated these parameters, would there be a way to either export the model so that you didn't have to have a data set or share with somebody else? And these are the parameters so that we can instantiate the model with those parameters or not have to do that?
He was asking if you fit a model and you want to share it with somebody else, is there a good way to share that? If the other person knows exactly what the model is, if it's a typical support vector machine, you might be able to give them the parameters. But the easiest way to do that in scikit-learn is to use the pickle module, because pretty much I think without any exceptions, there might be one or two exceptions. I think every model in scikit-learn can be pickled. So you do something like import cpickle. There we go. This is always dangerous doing something in real time, right? So, and we're going to do cpickle.dump s. Oh, I know why I did that. I need to. So I'm importing it, and the reason I ran that is because I want to use the tab completion, so it has to be imported already. Yeah, dump s. So this is going to dump the model to a string, and then you put the CLF in there. And now we've pickled this, and you could give this string, which looks like that. You could give this string to somebody else, and they could say, well, I want to CLF equals cpickle dot load s, I'll take that string, and hopefully it worked, yeah? Let's see if it worked. So we want to do clf.predict, and we'll just give it a 0, 1, 2, 3. So this is just, I just made up a feature here, and we'll see if it can predict. Yeah, so it predicted that this is the number 2 classification. So pretty much any model you do, you can do that. So you train it, you dump it to a pickle, either to a file or a string, and you can come back to it later. Yeah. Other questions? Yeah.
Another way that you could just take the string coefficients across the short and just load a new model and insert that into the model.
Yeah, he asked if you could just take that string of coefficients and just insert it into the model. That's a little more dangerous to do. It might work in some cases and it might not. Some models do some things in the background to like set flags that they've been fit, that sort of thing. So I wouldn't recommend that, but you could, if you really want to start hacking at it, you could probably do that as well. All right. So we've gone through this how to do classification, how to set up a classifier, and just to give you some examples to get your brain spinning a little bit on what sort of classification tasks you can do. You might think about email classification, labeling it as spam, as normal mail, priority mail. That would involve pulling out some feature vectors of the email, like bag of words type of things. You might think about doing language identification, labeling a document as English or French, categorization of news articles, analyzing customer feedback, face verification, things like that. So these are the type of interesting classification problems that you can do with scikit-learn. So again, I want to give you guys a chance to try this out. So try using, classify this iris data and use a different classifier. And I'm not going to tell you exactly which one to use here, but if you import linear model and then type linear model dot and then press tab, it'll give you all these different models that you might try to use. Logistic regression, orthogonal matching pursuit, all these different ones in here. And you can use the, so if we do orthogonal matching pursuit, you can use the question mark to kind of learn about it and what it's trying to do. But basically then you can instantiate that model and call the fit method, call the predict method, and see what comes out of it. I just want to give you a few minutes to try that out. And here I've listed a number of models on this site, on this page that you can, another number of classification models that you might choose from. Yeah.
So, where can I go to find out how to get all of these models and basically more in-depth analysis of how to go about
This question was, where can you go to find more about these models and how you would use them and more in-depth information? I would start with the scikit-learn website. So you go scikit-learn.org. And then I would, if you want to know about orthogonal matching pursuit, you can search it up there, and there's some documentation. Here's an example of using orthogonal matching pursuit for a certain problem.
So there's no book that you could recommend that says, that will take you through all of these different models and where they're working, basically how to trim down this giant list of models to, on classifying irises.
So the question was, so the question is there a good book a good reference book? And it looked like Olivier had an idea.
You can show a Vanderplas plug with a diagram.
Oh yeah, where is that?
Go and become vision.
Where is it? So, yeah, so Andreas is one of the main developers of scikit-learn, and he put together this flow chart that kind of shows you maybe sort of where to start if you want to do classification and what you might look at. So this is an interesting thing. There are also textbooks out there. I don't know exactly which ones to recommend. You know, the problem is machine learning is a field where people do their doctorates, right? So getting a basic introduction is kind of hard. You just kind of got to go out there and try things and gain the intuition about it. I see a comment back there.
There's an O'Reilly book called Machine Learning for Hackers that is entirely based in R, but is very accessible.
Okay. You mentioned the book Machine Learning for Hackers by O'Reilly Press. I've heard of that one. And it's implemented in R rather than Python, but very, very approachable. Yeah, one more.
It does not use scikit-learn, but it's programming collective intelligence.
Programming Collective Intelligence. Another O'Reilly book, Programming Collective Intelligence. And if you're an astronomer who wants to do machine learning, there's this great book coming out by Vanderplas et al. In a couple months that you might check out. But that's focused more on astronomy and other domain sciences. That's a great question. Yeah, one more.
I just want to see if there's any recommendation on a good text processing.
Recommendation on a good text processing book. Well, I'd start by going to Olivier's tutorial this afternoon. That would be a good start. There's some, I don't know of a book, but there's some text. There's a text processing with scikit-learn tutorial that you can find online. I might start there. Olivia, do you have a recommendation for a book?
The documentation is open source and it's kind of a book at the same time. So it's a good it's more like natural word processing. Depending on what you want to do with text, it can be a good option. There are many applications.
So yeah, lots of resources out there, and hopefully you can find the ones that will help you out. So we have about 5 minutes before our coffee break. Did everybody have a chance to instantiate a classifier there, a different classifier? I saw people typing away. No, someone didn't. I'll just assume silence means yes. So another thing real quick before we go to this break, another thing we can do in scikit-learn is probabilistic prediction. And this is only with some classifiers. And this is what it might look like. Logistic regression is a probabilistic classifier. This one's always confused me a little bit because it says regression, but it's a classification routine, not a regression routine. I think that's kind of for historical reasons. But if we instantiate a logistic regression classifier, we fit it, and then we can call this predict prob A thing. And I did something wrong. I didn't define x new, did I? Where did I make x new happen? Oh well. I will just make up an x new. 0, 1, 2, 3. So this is a very strange iris where the sepal length is 0. We'll see what it says about that. So this says among those 3 classification schemes, this iris is probably the third. It's 96% probability of being the third species, and 2% and less than 2% of being the first 2. And again, if we call predict on this, basically it just gives us the value where the maximum probability is. So just before we go to break, let's look at evaluating the model, and this will kind of be a teaser for what comes next. If we look at if we use the prediction and predict the labels for our training data here, And what we can do is say, check if the model, if the prediction equals what the true value is. And we see that in the case of probably about 95% of them, they're true, right? They match. But this has the same problem that we saw before, where we're basically evaluating the model on the data it was trained on. So for brand new data, for irises that this model hasn't seen before, we probably wouldn't expect it to be this good. And that'll come out in our cross-validation section that we do a little bit later. So it's 10:30 right now. We're going to take about a 20-minute break. You can go out and grab coffee and stuff like that, and come back ready to go around 10:50. And we will talk about model validation, cross-validation, and some more interesting machine learning things. So thanks. Hopefully you managed to grab some coffee and some juice in that gigantic line that was out there. But we're going to continue on with this. And just to give you a bit of a roadmap of the second part of this talk. Let me get back to my notebooks. So we have a little bit on unsupervised learning now. Some examples, kind of the same sort of thing that we saw with the classification and regression at the end of the last half, or at the first half. And then we're going to go into what I think is kind of the core of this tutorial, which is the validation and testing part, kind of saying how do you know how well your models are doing. And then towards the end, there's this number 10 and 11 that kind of have a more heavy exercise component. And I want to get to those exercises, so I think for this clustering and dimensionality, I'm kind of going to go quickly through them. So if I'm going too quickly, let me know, raise your hand and tell me to slow down. But I want to go through the information on number 7 and 8, but I think the 9, 10, and 11 are the really useful and really interesting parts of this tutorial. So we're gonna try to speed through to get to those, okay? So let's click on number 7, and this is a clustering example. So here we're going to look at an algorithm called k-means for clustering. And the idea with clustering is that you're given data and you don't have any labels about them, but you want to figure out which data are like other pieces of data out there. So for example, if you looked at a bunch of irises that were out in the field and if you're not a botanist and you don't know anything about them, but you measure all these features and you want to figure out which ones are similar to others. This is an unsupervised problem, and this is a problem where clustering is interesting. So did I skip one? Yeah, I did. I skipped 6. So we'll get to clustering in a second. Remember all that I just said and bring that back into your mind in about 10 minutes. First, we're going to do dimensionality reduction. So this is another unsupervised learning thing where essentially we had 4-dimensional data here, and if we had a way to do a 4-dimensional scatter plot that we could comprehend in our small human minds, that would be nice. But we can't really think in 4 dimensions. So in order to visualize data, often it's nice to be able to reduce that dimension in some way and plot the data so that we can see what's going on. And dimensionality reduction is an example of an unsupervised learning algorithm. So we're going to look at the iris data again. So we'll load the iris data set as we did before. And now we're going to use something called principal component analysis. And if you think back to when we first looked at the iris data, we were doing something like plotting the first feature versus the second feature, plotting the second versus the third, and just seeing what that looked like. PCA kind of takes that to another level. What it does is it looks for linear combinations of the features. So you say, we're going to take 0.4 times the first feature plus 0.6 times the second feature and call that one axis. And then the other one would be 0.7 times the third feature plus 0.2 times the first feature. You get the idea. You take these combinations where you're adding the features together and with some weights and plotting those. And what PCA does is it looks for combinations of features where the data has the largest variance. So variance means it's most spread out in space. And it's fairly easy to use here. If we can import PCA, we train the model as we did before. We're going to say we want 2 components, and we're going to whiten the data, which just means kind of like normalize the dimensions and make sure they're all the same. And if we fit the model, we get the model there, and we can look at these components. Remember what I said, the items with the underscore at the end of them are things that are fit during the model. So if you know anything about principal component analysis, these are kind of what we'd call the principal components. So these are the amounts that we're multiplying each dimension by when we represent them. And the interesting thing about principal component analysis is that it tells us how important each of the components is that comes out. So this is telling us that 92% of the variance, or roughly 92% of the information, is in the first component that comes out. 5% of the information is in the second component that comes out. And then we've thrown away 2 other dimensions that have less information than that. And we can see by looking at the sum of this, we can see that we've maintained about 98%, roughly 98% of the information in the data set while reducing it to 2 dimensions. So I'm sorry if this is really quick. You should read about principal component analysis if you haven't, because it's interesting. Most of my thesis work in astronomy was actually centered around something related to principal component analysis. So I get excited about it. But what we can do then is we can transform our data into this principal component space. And if we do that, what we get is something out. Let's look at the shape of this. So it's 150 by 2. And remember, our initial x, the shape was, got to print that. Let's print this. The shape was 150 by 4. So what this has done is it's taken our 4-dimensional data and projected it down to 2 dimensions. And 2 dimensions is something we can work with, right? We can scatter plot that. I'm going to skip this little piece here and go down to where we plot it. So again, we run Pylab inline to get the inline matplotlib plots. And I'm going to define this function to just plot components because we'll use it a couple times further down. But essentially all this does is that it goes through all the labels, and then for each label, scatter plots the data with a different color. So if we plot this now, this is what it looks like. So the colors here are the species of iris. And remember, we've taken the 4-dimensional data and we've projected it down to 2 dimensions in an unsupervised way. So that means this algorithm that did the projection knows nothing about these data colors. It knows nothing about the labels. It's just basically saying what's the most interesting set of dimensions. And the cool thing about this is that you can see that even though it's unsupervised, it doesn't know anything about the labels, it does a pretty good job separating out those labels. Like basically this first axis, the x-axis, is pretty close to what you'd want to look at if you were just looking at a single dimension that would help you distinguish between all the data, right? So this is an example of an unsupervised learning method. Remember, it knows nothing about the labels. We're just taking the data and saying, what can we learn about the data from the data itself? And we project it down to lower dimensions here. So just a quick list of some other dimensionality reduction techniques that can be used. The PCA, the randomized PCA, sparse PCA. There's several variants of all these things. There's an independent component analysis, which is it's actually related to that blind source separation problem that we mentioned before, like being able to pull out 2 different audio streams that are mixed together. And then there are a couple of manifold learning things, which these are nonlinear dimensionality reduction techniques that we'll get to see a little bit later in one of the exercises. Now I'm going to skip this exercise right now because of what I said before. I want to get to the more interesting things. But basically, this is the idea of dimensionality reduction. You apply some sort of filter. It takes high-dimensional data, puts it down to low dimensions. And 4 to 2 is one thing, but sometimes you have like 100 or 200 dimensional data, and you can get that down to 2 dimensions, and it really helps in visualizing what you have. Yeah. Yes, is it taking 2 of the features from the original 4, or is it combining them? And I went through that really fast, but it's basically combining them. It's asking, if you imagine, the way to think about it, if you think about you have a collection of points in 3 dimensions, you can rotate them and figure out which viewpoint in that rotation gives you the best view. And what this is doing is kind of the same thing. It's taking the 4-dimensional point cloud and finding the best rotation so that your 2-dimensional view of it is as good as possible. And
After you've got your PCA, how do you get back kind of what weights to assign to each dimension?
Yes. Once you have your PCA, how do you figure out what weights are assigned to each dimension? And that's what this components vector is right here. So this is saying that the first component on the scatter plot is 0.17 times the first feature plus minus 0.04 times the second feature, et cetera. So that'll tell you a little bit about it. It's a little more complicated than that because there's some normalization that goes on, but that's essentially what it is. So we'll have a chance, like I said, a little later to explore dimensionality reduction in a bit more depth. But right now, let's move on to clustering. So if you click on the 7th notebook there, and now you get to recall to your mind what I said about 5 minutes ago, 10 minutes ago. Clustering is about finding relationships within the data, things that are like each other. So again, we can load the iris data set, and all the stuff in this cell right here is what we did in the last notebook, right? We load the iris, we compute the PCA, we transform the PCA, and then we define the plotting function. So that's all from the previous notebook. And just to remind ourselves what we saw there, this was our PCA projection, right? We rotated the data to the space where it has the most variance. Now, the thing that might be interesting here is if we were to take out the red and the green and the blue and basically say that we don't have any label information about this, it'd be interesting to have an algorithm that could automatically find those clusters. Now, in the case of the red points, you'd expect the algorithm to do pretty well because they're pretty well separated. But for the blue and the green points, they're a little more mixed, so an automatic, unsupervised algorithm might have a little more difficulty with that. And what we're going to look at is an algorithm called k-means. And the way k-means works is it's kind of interesting. You specify how many clusters you think there are in your data, and then it kind of sets cluster centers through the data and asks, given these cluster centers, how close are these points, or how close are the points in the data set to those? And it assigns the points to the closest clusters. And then it kind of does an iterative thing and says, well, let's make the cluster centers the center of all the points that are assigned there. So it moves the cluster centers a little bit, and then reassigns the points, and then moves the cluster centers and reassigns the points. And you end up with an estimation of where the centers of the 3 clusters are in there. So fortunately, we don't have to code that up. It all happens within the scikit-learn estimator. And this is how we can do it. We can import k-means, and then because k-means involves a random initialization, we're going to use this random state object to give us a random number generator that'll be repeatable. And this should all start to look really familiar, right? We take the estimator, we instantiate it with some metadata here, or some hyperparameters, the number of clusters that we want. and then we call the fit method on it. And here we're fitting, just for clarity, we're going to fit on the two-dimensional data, the PCA projected data, just so we can see a little more what's going on. So we get out the k-means, and then as before, we have these attributes that come out with the trailing underscore. And in k-means, it's the cluster centers that are one of the attributes that are fit. So the cluster centers look like this. We basically say we have one cluster center at x equals 1.02 and y equals minus 0.7. So let's see where that is. That would be here and about here. So it says one cluster center there. Another cluster center at minus 1.29, minus 0.44. So that would be right about here, right? So that cluster found the red points. And again, and we can show the labels of the k-means classifier too. It basically says which cluster each point belongs to. So now if we use this information, we can plot the k-means labels and the true labels. And let me change the view here so we can get these on the same plot, the same screen. So above, the top plot shows you the labels that are automatically learned from k-means without knowing anything about the true labels of the irises, right? And the bottom labels are the true ones. So we can see something interesting here, that basically this left cluster k-means found pretty well. It distinguished it. The fact that the colors don't match doesn't really matter, because the colors aren't in any order. K-means doesn't really know whether this should be blue or red. It just knows that this cluster is out by itself. And then the other clusters, it doesn't do so well, right? There's a cutoff that goes this way in the real data, and the cutoff kind of goes horizontal in the k-means data. So it kind of shows you the limitation of some of these sometimes. It won't always really accurately give you the clusters that are the features that you expect. Yeah? That's a good question. He asked, did PCA really help in this case? And the answer is no to that, because we kind of threw away data, right? And the reason we ran this here on just the cluster on the PCA is just so we could visualize it a little better. But we could go back in here, and I was going to do that in a second. We'd go back in here, and instead of fitting to XPCA, we just fit to X, the full four-dimensional data set. And k-means can deal with 4 dimensions just as easily as it deals with 2 dimensions. So again, now if we show the cluster centers, it'll show the cluster centers in 4 dimensions. So it actually moves those clusters around in that 4-dimensional space and finds the optimal values. And just as before, we can see the labels are a little bit different. And now if we rerun this plot where we've used the full 4-dimensional data rather than the 2-dimensional data, we're still gonna plot with the projected data, but keep in mind that the clusters were actually on the 4-dimensional data. And this is what we see. So it looks like it's a little closer. In particular, you might have noticed before that the k-means, this top point up here at the top was joined with the other clusters when we projected the data down. But now that we use the full data set, this point seems to be in part of this cluster as we'd expect. All right, so that's the idea of how do you do unsupervised clustering with data. Yeah. Yeah, that's a good question. So he was asking if scikit-learn has a method for deciding the number of clusters that you can use. And that comes back down to the validation stuff that we mentioned before. So here in k-means, the number of clusters is a hyperparameter. It's something that you set before you fit the model. And based on your hyperparameters, your model parameters are determined. And we're going to talk, I think, in the next notebook about hyperparameter selection, how you choose the best hyperparameters. So with k-means, that's something that you have to do. There are other clustering algorithms in scikit-learn that do automatically determine the number of clusters. Like dbScan is an interesting example of that, which you can look up. And actually, while we're on the subject, let me go to the scikit-learn website. And I think there's a clustering example. Yeah. So this is just a visualization of, whoa, why didn't it, what happened? Here we go, clustering. So here's the clustering examples. This is the one I was thinking of right here. This basically takes a whole bunch of different clustering algorithms and feeds it some kind of interesting looking data sets and figures out what comes out. So on the left is mini batch k-means. This is similar to what we did. You just, you shift around the clusters and ask what it is. And then there are other things. There's spectral clustering, mean shift, affinity propagation. And you can see that each one kind of has different strengths and weaknesses in dealing with strangely shaped or oddly shaped data. And several of these, in particular, dbScan on the far right automatically chooses the number of clusters. And others, you have to set the number of clusters manually. But there are a lot of algorithms out there. Some of them are slow, some of them are relatively quick. K-means tends to be a relatively fast one, where some of these more sophisticated ones can take a while as you go to larger data set sizes. And once again, the strength of scikit-learn is once you know how to train the k-means estimator, you basically just import one of these other ones and do the same thing. You call the fit method, you call the transform method, you look at the labels, and the interface is pretty much uniform. So yeah, I mentioned some of these, but these are some of the clustering algorithms that are within scikit-learn. We have k-means, we have mean shift, dbScan, affinity propagation, spectral clustering, Ward. Anyway, so you can take a look at some of that on your own time. And there's lots of documentation in scikit-learn about how to use these and examples of them in practice. So some applications of clustering that you might see is building customer profiles. So you have a bunch of customer attributes in your data system, and you want to know what types of customers there are out there without having any labels on the data. You could group related news or related web search results. Google uses a lot of this sort of thing in their web results. Anything that's related, grouping related stock quotes, things like that. And also, clustering can often be used as a pre-processing step. So, you can use learned cluster IDs as kind of a feature for for some sort of supervised learning algorithm later on. So lots of different applications there. So there was an exercise, but I think we'll skip that as well. Actually, we did that. It was substituting the matrix X for XPCA, so your question got to it. Any questions about clustering before we move on? I know we kind of sped through that really quickly. Yeah?
In all the examples shown, dbScan appeared to be better than the other algorithms. Is there an advantage of the other algorithms besides speed?
As she said, in those examples we showed, dbScan seemed to outperform everything else. And the answer is that dbScan is really slow. So as you go to high data dimensions and high numbers of data, I forget the exact scaling, but that's why you wouldn't use that in some situations.
There's also fewer divisions. If you look at some of the other algorithms that are actually dividing the data, and depending on what that data really was, there's some human mistake. You see how the affinity propagation, you got to kind of define it in quarters.
Yeah.
That is the data. What the data is divided into those models.
Yeah, that's a good point. He was saying that it's not let me make sure I get this right. It's not always obvious how you want the data divided, right? So in affinity propagation, you might actually want the data divided into quadrants. And if that's the case, you basically need to look for an algorithm that is, use an algorithm that's looking for the type of features that you're interested in. And that's where intuition about how the algorithms work internally, it can be helpful. So. Actually, dbScan is not that much slower than the other ones, according to this. There's some spectral clustering is a little slower. It shows the times in the bottom corner. No, this is all there is on this page, but there are more examples of clustering in scikit-learn that you can see. Right, other questions right now? Well, let's move on. We have about an hour left, a little more than an hour. I'm going to skip over this number 8. This is an interesting exercise that you can try at home. It's basically a little graphical user interface that allows you to interactively try a learning model. I'm going to skip that right now and go into this validation and testing thing. 'Cause like I said, I think in my mind, this is the most important piece of this tutorial, because you can go out and you can use these models and you can take your data sets and try to learn the features of new data. But the real question is deciding how well you're doing at that, and also deciding what the next steps should be. So yeah, let's just jump into this here. We have the iris data, right? And this is all stuff we've seen before. We're going to use the linear SVC classifier and fit it. And then we're going to look at whether the predicted values on our training data set match the true values. And we've seen several reasons why this is a bad approach, right? Because we're checking the performance of the estimator on values that it was trained on. So the best possible estimator here would be to say, have I seen this data before? If so, then return that label. If not, then return something random, right? So that would work really well in this case, but that's not what we want in practice. We want our classifier to be able to generalize to data we haven't seen before. So this is where cross-validation comes in. And as someone over here alluded to before, the way that we can approach this is to split our training set into two samples. We have the training set that we'll train the model on, and then we have the test set where we know the true labels, but we're not going to train on that, and we'll use that test set to evaluate the model. So scikit-learn has this built in, which is really nice. It has a cross-validation module. So you can do from sklearn import cross-validation. And we're going to use this train test split function. And this will essentially, this will split our X and Y data into a training sample and a test sample. And we'll say the test size is 0.25, so about 25% of the data in the test sample. Now the question of how much data goes into your training sample versus your test sample is kind of a matter of taste. Now, some people might do 50-50, some people might do 90-10. It also comes down to the problem that you have, how much data you have. If you only have 10 samples to begin with, you might not want to throw away 5 of them in your training, right? So, but if you have 1 billion samples, it doesn't hurt to throw out 100 million or so, or 500 million or whatever. So this is the approach that we'll use for validation. So we get these out, and we'll just confirm that the input data was 150 by 4, the training data is 112 by 4, and the test data is 38 by 4, right? So then we can fit our linear SVC on the training data, X-train and Y-train. We predict the testing data, and then we can print this y predicted equals y test. So now this is a better representation of how well our classifier is doing, right? There are a few falses in there, but mostly true. So just kind of in general, we can look at that and say our classifier is doing pretty well. It's for data it hasn't seen before. It's about it's over 90% accurate, right? There's three wrong answers out of about 40 values. So that's the idea behind validation and cross-validation that we'll get into. But as we dive deeper into this, there's some interesting things that come out of this, right? So let's say you do cross-validation or you do validation on your data set in this way, and you find out that it's not performing as well as you want to. So you have this iris classifier, and it's only correctly predicting 50% of unseen irises. So what do you do in that case? This is where the kind of the rubber meets the road in machine learning. And you can think about this in terms of my field, astronomy. So say you've gone out and you've observed 10,000 galaxies, and you've figured out their masses through some other measurement. And now you want to know how well you can predict the mass of a new galaxy that you just observed with your telescope. And you find out that you're not accurate enough. You're not accurate enough to do the science that you want to do. What's the best thing to do? Do you try a new model? Do you search for more training data? Do you go out and observe more galaxies? Or do you go back to the same galaxies and observe different features for them? And this is a real question, right? Because telescope resources are really, really expensive. So it's not just a theoretical thing. This is like how do you spend your money wisely in trying to get the scientific results you want? And you can think about the same thing in case of Google. Should Google spend their time if their web results are not web search results are not as good as they hope them to be? Should they spend their time? Should they get more CPUs so they can compute more complicated models more quickly? Or should they get more disks so that they can store more data and have more training data to learn from? And it's a real question. It comes down to dollars and cents and how you spend your resources. So that's why I think this is the most important part of this tutorial, because it's the stuff that you can use these algorithms, but this is how to go the step further and reason about how to actually, in the real world, how to actually recommend what to do next or how to spend your time to improve your results. And I should say that the content of this section, I adapted it pretty heavily from Andrew Ng's Coursera course on machine learning. And if you ever have a chance, if you want to dive deeper into some of the math behind machine learning, that's a great place to start. It's one of these free online courses, and he's a really excellent teacher. So you should check that out if you're interested. But basically, we're gonna develop the tools here to answer that question. If our estimator is underperforming, do we use a simpler or more complicated model? Do we add more features to the data, or do we add more training samples? And the interesting thing about this is it's often counterintuitive. There's some times where your model is underperforming, and even if you add billions more data samples, there's no way you're going to improve your result. And it's good to know that before you go out and spend $1 million trying to get more data samples, right? So what we're going to look at here is a simple regression problem. So like most of the stuff we've seen, we're going to look in low dimensions, small amounts of data, but all of this generalizes up to large amounts of data pretty easily. So we'll do the PyLab inline to make our figures appear in line. And what we're going to look at is some X data. This is randomly scattered, 20 points randomly scattered from 0 to 10. We're going to create a polynomial. We're going to create a polynomial, x squared minus x plus 1. And we're going to use, in lieu of the scikit-learn estimators here, we're just going to use a simple polynomial fit. And NumPy provides that. So if we do this polyfit right here, we can see that the polyfit recovers the input here. You know, we have 0.5 times x squared minus 1 times x, and 1 times 1. 1 times x to the 0. So, and we can also visualize the result. We'll get a new X array from -1 to 12. We'll evaluate using the polyval function, and then scatter and plot the result. And this is what it looks like. So basically, you can think of this as a regression. Even though it's not a scikit-learn classifier, it's a regression problem, right? We have X data and Y data, and given new X data, we want to know what the new Y data is. And the new Y data is that curve that goes through it. So the interesting thing to note here is that the hyperparameter we've chosen is the degree of the polynomial, right? So if I change this degree of the polynomial to 1 and redo all of this stuff, then it's fitting a line to this curved data, and it doesn't do so well. So that degree, that's the hyperparameter, and this is kind of you can think about this as the knob on the model that we're turning to see how well we can fit the data. So this gets a little more interesting if we add noise to the data. So here we're going to do the same thing. We have the same model, 0.5 x squared minus x plus 1. But we're going to add some normally distributed noise about that. And then we do the polyfit again. We compute x new and y new, and then we scatter, and we'll also print the RMS error. So you can see here that the degree 2 model fits pretty well, but the interesting thing here is, if you do this with me, if we change the degree, watch the RMS error. So RMS is 1.7, so that 0 would be perfect, 1.7 is all right. If we change it to 1, we can see that, oh yeah, the RMS error is way worse with a degree 1 polynomial, right? But what if we increase the degree? We know that this, why is this highlighted? Why doesn't that highlight go away? There we go. We know that this fundamentally is a degree 2 polynomial. Then that's because that's what we put in. But what if we start going to 3? Watch the RMS error. It's 1.7 now. Now it's 1.5. So a degree 3 polynomial fits our data even better, right? So why not a degree 5 polynomial? 1.4, that fits even better. So we could say, well, the best model is just a high degree polynomial, right? So we got a really small RMS error by doing that. And as we go higher and higher, we can get really ridiculous here. Degree 200 polynomial. And theoretically, this should be 0 RMS error right now because there are enough free parameters to fit all the points perfectly. But it's just numerical accuracy that makes it different. But yeah, but clearly, this is not the result that we want, right? So just looking at the RMS error is not telling us what we want, because any new data here would just not be in the right place, right? So this shows us a little bit of the bias variance trade-off. So again, I'm going to plot a little figure here that I wrote code for, just to show you what's going on. If we have some data that looks like this, a biased model is one that no matter how much we change the model, it'll never fit the data well. So the model itself is biased. On the right side, we see a high bias model. If we try to fit a line to this set of curved points, then that line will never fit the points, no matter how we adjust the parameters, right? On the far right side, we see something different. This is what we call a high variance model. And a high variance model can often fit the points perfectly. But the reason it's called high variance is because if we were to perturb one of those training points a little bit, so for example, if we took this point and moved it to the side, moved it to right there, then the model would change drastically, right? It would still fit through all the points, but it would not look the same at all. Whereas in this one, if we perturbed this point to the side right here and moved it there, the best fit model would probably stay pretty much constant, right? So the issue you have with most learning problems is you're trying to trade off between bias and variance. You have these models that don't depend very highly on the data on the left, but they don't fit the data very well. And on the right, you have models that fit the data perfectly, But depending on which data you put in, they vary a lot. So high bias versus high variance. And the key to actually doing machine learning in practice is to figure out when you have a high bias model, when you have a high variance model, and how to move forward in the most effective way. Does that all make sense? Any questions right now? All right. So one way to do this is something called validation curves. So we're going to create a data set like the above example. It's just kind of a simple curve with some random noise. And we'll do some evaluation on that. So what we're doing right here is we're doing a random, normally distributed noise. And the mean value is this 10 minus 1 over x plus 0.1. So that's the function. It actually looks a whole lot like this right here, these data. And then the error is the amount of scatter about that function. So that's our test function that we'll use to generate this data set. And then we just have a function to compute the error. So given an x and a y and the result of the polyfit function, we compute the error. It's just the square root of the mean of the squares. So the root mean square error, RMS, right? So what we're going to do here is we'll take 200 points, and we're going to use about half of them for our validation. We'll sample random x values and then evaluate the y values on those, split them into training and test, and then scatter the two portions. Right, so let's run this. And something went wrong. What did I do? I forgot to define these. Enter. So we can see that our test data and our training data, one of them is blue. The test data is blue and the training data is red. They're kind of drawn from the same distribution, which is what we want. We want them to kind of be the same type of data. So given this validation set now, we can do what we were saying before and predict how well our model is doing. So let's look at this code. And what we're going to do here is plot not a cross-validation curve, a validation curve. So take a look at what we're doing here. We're going to do degrees from 0 to 21. So this is our hyperparameter that we're fitting, the degree of the polynomial. We'll do a polyfit on the training data. That's kind of fitting our learning model, right? And then we're going to compute error on the training data. So this is the bad way to do it. This is where it allows it to be overfit. And then we're going to compute error on the test data and then plot the results. So let's take a look at this. And then I also plotted the dotted line, which is kind of the input error distribution that we put in there. So this is a pretty typical validation error plot. So what we see in the blue is the error on the test set. This is the set that the model was not trained on, right? And it goes down and reaches a minimum and then starts going up again. And what's going on there is that when the degree of the polynomial gets up to 20 or so, then we're in the regime where the model is overfit. You know, it's kind of wiggling all over the place. And any new data is very unlikely to be right on that curve. And in the regime on the far left, we're basically fitting a straight line to our curve data. So it doesn't fit either the training or the test data very well. So that's the blue curve. It hits that minimum and then goes back up. And then the training error just kind of continually goes down, right? We saw that as you increase the degree of the polynomial, you fit the training data really, really well. You have this kind of wildly oscillating curve that happens to go through every point. But that doesn't mean it's a good model. So what we want here is we want the best model that we can see is the place where this validation error is minimized. Not where the training error is minimized, because that would go on forever, right? But we want to minimize the validation error. Does that all make sense? Yeah.
Do you find that usually the RMS or the errors
Yeah, he was saying, he was asking about the different formulas to compute the errors. Here we used RMS, and like there are other options that you can use to compute errors, and we'll actually see that a little bit later. It depends on the algorithm, and it depends on your taste, and it depends on what you're interested in seeing. But I think the standard fallback would be the RMS, and then if you have reasons to use other things like L1 loss or some of these more robust loss functions, you can use that as well. Yeah. Any other questions right now? Okay, so this is our validation and our training curves. Another thing that you might be interested in is, well, you know, as we increase the number of training points on this, it might change the results, right? So there's something called that Andrew Ng calls learning curves that are pretty interesting in evaluating this. So this is answering the question of as you add training points, what's going to be the effect on the model error? And the way that you do that is you basically iterate through, and you first train your model on 10 points, and then you train it on 20 points, and then 30, and then 40, and you go all the way up until you have your full training set. So this is our, we're going to define this function here that does this, plot learning curve. And so we'll do sizes from 2 to n, and n is the total number of points, spaced by, we'll do 50 different sizes between 2 and n. And then we loop through and we do the polyfit of the training up to that size and the y up to that size. And then this is the important part. We compute the validation error on the full test set, and we compute the training error on only the part that it was trained on, right? Because if we computed the training error on the full training set, then that would mean there are points in that weren't part of the training set, right? So we want to make sure that the training error is just computed on the points that were in that particular training set. And then again, what we'll do is we'll plot the results here. So we've defined that function. So we're going to plot the learning curve for d equals 1. So this here says that on the x-axis is the training set size, and the y-axis is this RMS error, and we're holding d equals 1 fixed. So let's think about what this says. This is also pretty typical of what a learning curve looks like with most models. So if you do your training set down to, say, 2 points, think about trying to draw a line through 2 points, right? You're gonna be able to fit them exactly. So that's why we see the green curve on the left. There's 0 error because you could just draw a line through 2 points. But as you add more and more points, the line gets to be a worse and worse approximation of that. And eventually it sort of levels out, and you get to the place where no matter how many more points you add, the fit to the line is not going to get any worse. It's all kind of, so it kind of averages out there. So that's for the training set error. For the validation error, think about this. We take 2 points from the training set and we draw a perfect line through it. And then we choose a point that wasn't part of that set, and it happens to lie out here, right? It's going to be really far away. So that's why the RMS error is really high for the low numbers of training samples. But as you get more and more training data, that the model gets closer and closer to actually reflecting what's happening in the data, right? So the validation error is basically going to be a curve that's always decreasing, where the training error is always increasing. And if you think about that a little bit, you can convince yourself that that's probably a good assumption, that the training error will always be increasing. As you add points with a not very good model, you're always going to get slightly worse fits. Validation error is always going to be decreasing. So this says with d equals 1, with our d equals 1 model, what's going to happen as we start, if we increase this to 1,000,000 points, would we get a better training, or would we get a better validation error? It looks like we wouldn't, right? Because basically we have this lower bound and this upper bound that are converging. And we can kind of say that even if we increase this out and we go out forever this way, we expect it to kind of converge right there. So if we want, if we say this is a model and our specification is that we want the error to be around 1.0, this model is never going to do that, no matter how many training points you have, right? So this kind of gets back to that thing. If I'm looking at galaxies and I have this learning model to try to figure out the mass of the galaxies, and my model's not, my validation error isn't as good as I want, I could spend $1 million going out to and on a 10-meter telescope to try to observe more deeper galaxies and get more data. But that would be a waste, right? With this model, it's just not gonna happen. It's not gonna work. So does that all make sense? So this is where it gets really interesting, right? So now we can say, well, what if we do a d equals 2 model? Well, that's getting a little better, right? We're converging down a little bit. D equals 3 model. Yeah, that's getting much better, closer to our number 1. And this dashed line, remember, is since we generated this data set from scratch, we know that basically the best possible RMS you can do is around 1. So that's why I drew that dashed line. Now, as we go to, whoa, it's getting big. So I was going to do this down here. Yeah, as we go to higher and higher D, though, now watch what happens here. So this is a little noisy, and it's because our data sets are kind of small. It has a lot of noise in it. But you can basically see the trend here is that the space between the training error and the validation error is much larger for these high D models, right? If we look at d equals 2 again, and this is on the same scale, the space, they're really close together. So for d equals 2, as you add more and more data, you don't expect them to get much closer together than they are. But for d equals 20, they're really far apart, and you might expect if this decreased trend and increasing trend continues, you might expect for d equals 20 that adding more data would actually help you out, right? Because these two curves are kind of, as you go along, they're getting closer and closer together. And eventually, the best model is the one where these are very close together at the end. So this says that if your model is a complicated one like this d equals 20 model, then you can actually do better to either add more data, or you can do better by simplifying it, right? If you go down to 10 to 15, then 15 does a little bit better. It kind of converges. And now you should think in your mind that these two things we did the learning curves here, and we did the cross-validation curves here. And these are two slices of something that's going on in 3 dimensions. We have the number of points, we have the degree of the model, and then we have the error. So if you fix the number of points and slice through the degree of the model, this is what it looks like. If you fix the degree of the model and slice through the number of points, then this is what it looks like right here. So you're kind of trying to find the optimum on this like 3D surface, right? So this is how you can go ahead and answer that question. Given a model that's underperforming, what's the best thing to do? In the case of d equals 1, is that what I wanted? Yeah. In the case of, let's do it up here because the axis is a little better. In the case of d equals 1, we can see that keeping our model as is never going to be a good idea, is not going to give us any improved results, right? So we need to make the model more complicated. But say in the case of d equals 20, we can see that we might be able to get a better model by actually get better results by actually making the model simpler, right? Because we can pull down that blue curve given our training set size. Or alternatively, we can keep the model complicated like this, but just add a whole lot more data. And that'll eventually get that blue curve to go down. Because what we want is that blue curve to be down low eventually. So this is a way to answer that question of how do you go about in reality working with machine learning and figuring out how to best move forward. So just in summary, I want to kind of pound this in. What you have is a high bias model. That's the one. Think about having a curved set of features that you're fitting a straight line to. A high bias model, if you add more features, it's not going to get any better, right? Because the model just can't fit the data. Sorry, if you add more training samples, the model just can't fit the data. So the thing you can do if you have a high bias model, and remember the high bias model looks a lot like this in the learning curve. It just, the curves have converged together. If you have a high bias model, you can add more features. So it's kind of a way of making the model more complex if you have more observations of each object. You can use a more sophisticated model. In this case, we were turning up the degree of the polynomial. But in some models, there are other ways to make it more sophisticated. You can use fewer samples, actually. You don't even need to use all the number of samples that you used. You could, if it's computationally expensive to use 1 million samples, with a high bias model, you could actually go down to 500,000 and you'll be just fine. Or you can do something, decrease what's called regularization. And we're not going to talk about that, but if any of you guys return to read more about machine learning, regularization is basically a way to impose simplicity in learning models. And if you decrease that, it allows the model to be more complex. So on the flip side, the high variance models, remember the high variance models kind of look like this. They fit the training data really well, but they fit the validation data really poorly. Think of, you have a few points with this wildly oscillating line going through it, and any new data is not going to be fit very well. The high variance models, what you can do is use actually fewer features. You could use feature selection to decrease the number of features, perhaps. You could use more training samples. If you have the capacity to go out and find 1 million more samples, then that'll help with a high variance model. Or you could make the model more simple. You could increase the regularization to impose simplicity, or use some other way to make the model simple. Right? So I'll go over that. And one last caution I want to say. So this whole time we've been talking about the training set and the validation set, right? And how you have to prevent against overfitting. Overfitting is this high variance model where the model becomes too close to the particular data set that you're using. And the interesting thing is you can actually overfit the hyperparameters too, right? So given our data set, if we tune our hyperparameters so it's perfect on our validation set, so we say the degree of the polynomial is 5 or something like that, and it fits our validation set the best way possible. It's possible to actually overtrain those hyperparameters on the validation set. So in that case, you need a third set, which is often called the test set, where once you've done the training and you've done the validation, then you use the third set to evaluate how well your model will do on some new data. So that's just a caution that you should keep that in mind as well. So I kind of blew through that, and that was mostly me talking at you, and I'm sorry about that. But are there any questions on that before we move on to some exercises in this area? Yeah.
Yeah, I do have just one question. So in the simulation you were running with, when you were changing the D, it was always one spike that went up. Is that just sort of like an artifact from the data set, or is that something that?
Yeah, he was asking about, in this example, there's always one spike in a particular location when I was changing D. And that's basically just an artifact of the data, yeah. I thought about doing this with fake curves that are nice and smooth and show what the general trend is, but in reality, you rarely see that nice general trend. There's kind of this, especially when you're dealing with small training set sizes on the order of 20 or 40, you'll see that sort of variance in the data. Yeah. All right. Cool. We have about a half an hour left, and I'm excited because now we can get into some of the cool things. So we might have time for only one of these. So maybe by a raise of hands, would you rather go through classification of digit images, or would you rather go through a problem from astronomy that has some really interesting science into it? So raise your hands for astronomy. Raise your hands for digits. I think astronomy wins. Yes. I clearly framed that correctly. So click on number 11, and this is the photo-Z regression example. I'm so glad you guys chose this. That was awesome. So this is an example from, like I said, from astronomy, where we're doing something called photometric redshifts. And I got to give you a little bit of background on astronomy to tell you why this problem is interesting. So we'll run Pylab inline again, and then import this plotting function. And this right here, this is another one where it's downloading maybe a couple hundred kilobytes of data. So if you haven't already downloaded the data, it might hang up on this with everyone trying to hit it at once. But so basically, this is what astronomical data often looks like. So we have something here where the y-axis is the flux and the x-axis is the wavelength. So the black line that you're seeing here is the spectrum of the star Vega. If you look directly overhead in the middle of the summer, Vega is the bright star right in the middle of the sky there. And so the wavelength is basically the color of the light, right? This is 3,000 angstroms all the way up to 10,000 angstroms. And the black line tells you how much energy there is at each of those fluxes. So astronomers use spectra often, and you can get a lot of information from spectra. Those little dips in the lines there, that's actually absorption from hydrogen. So we can learn about how much hydrogen is in the atmosphere of these stars by looking at the spectra and many other things. But it turns out spectra are really complicated and difficult and time-consuming to get. So another thing that astronomers do is they look at photometry. And what photometry is imagine these colorful filter curves right here. You take all the flux within that region of the spectrum and just report it as a single number. And the advantage of photometry is it's really fast. You can do large swaths of the sky really quickly, but you lose some of the information because you only have 5 numbers for each object instead of 1,000 numbers for each object, right? So that's kind of the basic astronomy stuff that we'll go into. And the problem here is something that we call photometric redshifts. So, put on your Albert Einstein hat right now and think about the universe expanding, right? In general relativity shows that there's this big bang, and then the universe has been expanding ever since. And in that expansion, the wavelength of light gets stretched out the same way when there's an ambulance going down the street. It comes at you and it's going wee. That was my great generalization. But so that Doppler shift of sound is really similar to the sort of Doppler shift of light as the universe expands. So galaxies that are further away have their light stretched out more than galaxies that are closer. And what that looks like in terms of spectra, actually I'll do this right down here. If we plot the redshifts, what that looks like in terms of spectra is basically these spectra are shifted. We call them redshifted because they get redder. The peak of the spectrum as you go out to different redshifts are usually called Z in astronomy, is that the spectrum moves. Now if you have most spectra kind of have this general shape. If you observe the entire spectrum, it's fairly easy to tell what redshift it is because you know where hydrogen is supposed to absorb energy. And if the hydrogen absorption is moved off to the side, you can compute the redshift. But we don't have spectra for everything out there, especially the faint objects. We only have the photometry. So that means that we're looking at just 5 numbers for each of these spectra. But you can see that there is some information there. Like for example, the Z=0 galaxy is very bright in the G and very dim in the I band. You see that? And then the Z=0.8, the red spectra, is relatively dim in the G and very bright in the I. So you might expect that just with those 5 numbers, rather than using the whole spectrum, just using those 5 numbers, you could actually estimate the redshift, right? And this is the photometric redshift problem. We can do spectroscopic redshifts easily. Photometric redshifts are hard. And this is really important because as we learn more and more about the universe, the way that we're pushing the boundaries of our knowledge is to observe fainter and fainter galaxies and construct models of the universe that depend heavily on the redshifts to those galaxies. So we need to be able to very accurately do photometric redshifts. And this is a regression problem, right? We have 5-dimensional data. We have a number of samples, 5-dimensional data. And for some of them, we have spectra. We know they're redshifts. And for others of them, we don't have spectra. So they're unknown, and we want to predict the label. The label here is the redshift. Does that make sense? Yeah. So this is, just like we were fitting a line to data earlier, this is a regression problem that has real consequences because it keeps me employed. No, but it's a regression problem that can actually help us learn about things like dark energy and dark matter and some of these fundamental aspects of the universe, of cosmology, that I find, frankly, pretty fascinating. So this is the problem that we're going to go through here. So I've kind of gone through this motivation here. And what we're going to do is return back to this decision tree regression that we saw briefly earlier. So I'm going to run through this really quickly, kind of a basic model, and then set you off, and we'll have about 20 minutes for you to go through this exercise and do some astrophysics. I bet you didn't think you were going to do some astrophysics today. So we'll fetch these galaxy mags, and again, this is one that hopefully, if you got it's about 3 megabytes, so hopefully if you got the email and looked at the site earlier, you downloaded it. If not, you might be able to pull it off the memory stick that's out there. So if we look at the data, we have the shape of the data is 50,000. So there are 50,000 objects in here. And the D type, this is what we call a record array. So it's kind of a compact way of storing all this data. We have the U, the G, the R, the I, the Z bands. These are the filters. And the spectral classification, which is some interesting information, the redshift, and the error in the redshift. So we're going to ignore for now the spectral classification and the redshift error and just focus on the photometry and the redshift, right? So for historical reasons, astronomers usually don't work with the raw magnitudes. They normalize them and do something called colors. So we're basically taking each magnitude and subtracting its neighbor. And that gives us some more normalized information. So what we have here is the redshift, which is our unknown, right, our label. And then we have the colors, which is 50,000 points in 4 dimensions. And just like before, we can split this into training and validation sets, right? We'll use the decision tree regressor and set up that classifier. And then I think I skipped over this before, but this is kind of a way to do, this is kind of a way that scikit-learn has to do validation automatically. You don't always have to do it by hand the way that I showed earlier. We're going to do a cross-validation score, where basically what this does is it takes 3/4 of the data, evaluates it on the other quarter, and then takes another 3/4 of the data and evaluates it on the other quarter, and then repeats that 2 more times. So you've basically kind of cross-validated. You've used each piece of data as both a training and a test set. And we can see that our score is about 0.72. So this is a score that's telling us how well we're doing. We're between 0 and 1. And 1 would be perfect, but we're right at about 0.7. So this says that our decision tree is not doing very well. This is not good enough. And we can see this by plotting the redshifts. Sorry, I'm speeding through this a little bit. So we're fitting and predicting, and then we'll plot the test versus the predicted. And this is what it looks like. So the true redshift is on the x-axis, and the predicted redshift is on the y-axis. We do really, really well for some galaxies, but not so well for others. And that's kind of a feature of photometric redshifts that we see in practice. These ones that are outside the dotted lines, we often call these the catastrophic outliers because something went catastrophically wrong in our fit. We're off by a whole lot. So let me remember what we were doing here. I just recalled this is much longer than I realized. Yeah, it's fine. We have time for it. So let's optimize the model now. So we can do this learning curve thing we did before. And just like the degree of the polynomial is something we can adjust in the polynomial fit, this max depth of the decision tree is something we can adjust here. So we'll do a max depth array. We'll get the training error and the testing error. And we'll loop through the max depth array and instantiate the classifier. We'll fit it. We'll do a prediction on the training data, prediction on the test data, and get the training error and the test error. And this is just what we saw before, and it takes just a second to run because we have to run all those models. And this should look familiar. This is the type of thing we saw before. The training error, as you increase this max depth, keeps going down and down. So we're overfitting the data going down here. This is the curve that's wildly oscillating going through all the points, right? And the validation error kind of comes and hits a minimum and then goes back up. So this tells us that the best value is somewhere around 10, right, for the max depth. I'm going to skip over that, but you can read about that later. So plotting this optimal model, if we look at the max depth of 10, we can plot the redshifts and we see this. Now this is a little bit unexpected, right? But the thing about this is that the RMS down here in the corner, 0.23, this is actually better than what we saw before. The RMS here is 0.26. So our algorithm is doing what we asked it to. It's minimizing the RMS. It did minimize the RMS, but the results look not at all like what we'd want them to look like, right? So this comes back to what you were saying, is that what we're looking at is the wrong loss function here. The loss function is not giving us the model that we'd want it to give us. So we'll propose an alternative loss function. And here, since what we're really worried about is these outliers, right? These catastrophic errors. Let's just do a loss function that just tells us the fraction of points that are greater than off by more than 0.2. This is just something, we take the sum of how many points are greater than the cutoff and then divide it by the total. So we'll call that our outlier fraction. And we'll do the same thing again, where instead of putting in the RMS error, we do the outlier fraction, go through it, and then plot the results. And this is the curve we get. And it's interesting that with the outlier fraction, with this different loss function, the best model is a much deeper tree, right? Our minimum was at 10 with the RMS, but it looks like it's about 19 or 20. Or probably maybe even beyond that with the outlier fraction. So we can do that. We'll set our max depth to 20, do this fit, and we get something that, yeah, it's better than the last one, but we still have all these catastrophic outliers, right? So thinking about what we talked about before, the learning curves and things like that, what do you suspect is the best way to move forward here? Do you think this is a high variance model or a high bias model at this point? Why do you say high bias? Who said that? Yeah. Yeah. So we already went through that validation thing and tried to find the optimal, right? And,
High variance and high bias.
Olivia says it's high bias and high variance. Why is that?
You have a big gap and a bad training error.
Yeah, so we also have a big gap between. So that's good. Yeah, so we still have this big gap here. So right. So it's some combination of high bias and high variance. But I think to move forward here, we do need to improve the model, right? And that indicates that it is biased. So this is where we're gonna start thinking about this and actually plot the learning curves for this and figure out how to move forward. So there are two exercises here, and the first one, I actually haven't done these exercises, so I don't even know what the answers are going to be, but I want to give you guys a chance to look through that. The first one is optimizing the data, asking, is this a problem with data? Do we need to add more training samples in order to get good results here? And that'll involve going through and plotting the learning curves like we did just a few minutes ago, and seeing where the bias and variance hit on that number of samples versus training error. And the second one is just seeing what we can do with other learning methods. So rather than using a decision tree classifier, we can use something called ensemble methods, like a random forest. And essentially what this does is it takes a whole bunch of decision trees all at the same time and uses them to decrease the overfitting. And you can actually get better results from that. So I'll let you guys choose, maybe with someone next to you, a partner or two, figure out which one of these you want to work on, and then see if you can do this for. So number one is kind of the giving the recommendation for the best way to proceed based on learning curves, and number two is trying a more sophisticated model and seeing if you can get a better fit to the data. So we have about 15 minutes left, which is probably not enough time to go all the way through this, but I'll let you guys go for it and see how far you can get. And I'll be walking around and answering questions if you have them. So good luck. So hopefully Olivia's tutorial this afternoon will address some of the big data aspects of it. If you have any questions about scikit-learn, the email list is usually pretty good. There are a lot of folks on there who are really interested in helping get people up to speed and learn some of these models. I actually wanted to say real quick that I remembered I had done this last thing. I have done something similar to this. This is a website, astroml.github.com. This is kind of an astro machine learning package that I worked on. And it also has figures from our book that's coming up. And in the classification chapter down here, we do decision trees. And here's photometric redshifts by random forests, and kind of on a bigger data set. But it shows you similar to data to what we were just working with, and shows the cross-validation and the training error and how it's scaling. This one, you can see that, well, I won't talk about it too much, but you can dive into that. Last thing is that there is a survey where you can talk about how good or bad I was at doing this tutorial. And where is that? I think it's in the preliminary notebook here. All the way at the bottom, there's a survey evaluation. So if you have a chance in the next day or so to fill that out, I'd appreciate that, just to get feedback, because I enjoy doing these tutorials and I'd like to make it better next time if I can. So thanks very much, and I'll send you off to lunch. Thanks for coming.